the direction of this r, in 2D space, in two-dimensional space. Now, 3 and 3 are two integers. I have to take the smallest integers in the ratio. The ratio is 3 to 3, so it is 1 to 1. Okay, so if I take it as in two dimensions, put these in square brackets like this, then this point, this direction here, is a direction 1, 1 in 2D. Of course, this direction is the same as if I take this point here, because this point is 2a plus 2a, 2b, right? So again, this vector from the origin to this point here, okay, is 2a plus 2b. So the ratio of 2 to 2 is 1 to 1, and again, it's the 1, 1 direction. And again, if I take this point here, again, the same direction, it's going to be 1a plus 1b, and the smallest integers in this ratio are going to be 1, 1. So all of this direction, and even if we extend it further, okay, it would all be 1, 1 direction. So that is, and if we take three-dimensional case here, if we write a vector as n1a, n2b, n3c, then we take the numbers n1, n2, and n3, and take the ratios, and take the smallest integers in this ratio, that would define our direction. Okay, so that is literally how we define a direction. So to recap all of this, and again, as I said, all directions for all points are equivalent directions. Okay, we place a bracket like this one for equivalent directions. And equivalent directions actually are all directions which are indistinguishable when we look at the single crystal. Single crystal is a regular periodicity. So there are so many directions that are the same, even though they point in different directions, but they're equivalent in the sense that the arrangement of atoms around them, everything, the morphology, is exactly the same. So you label them as equivalent directions and you put them in a pointed bracket like this one. This example here hopefully gives us a good illustration of how to work out planes and how do we define equivalent planes, etc. And what we have here is a simple cubic structure. So we have SC structure, which is shown in this figure here. Now we want to find the Miller indices. Miller indices define planes. So we want to find the Miller indices for the planes C, G, H, D. So this back dotted plane. How do we find the Miller indices? How do we define this plane? Now, what we're going to do is I'm going to take point A as my origin. And then at this point A, I'm going to draw the three basis vectors. One along AD, okay? So one of the vectors is along AD, A, and then another vector is along AB, which is the vector, or along AE, which is the vector B, and then the third vector is along AB. And remember, A, B, C are in right-handed system. What do we mean by right-handed system? Okay, so the right-handed system meaning if you rotate, okay, from D to E, okay, if you rotate a corkscrew, or a screwdriver from A to B, it will proceed in the third direction, C. So that is what we mean by right-handed system. Okay, so ABC is a right-handed system, okay, and it runs from A to B, and it proceeds in the C direction. Now, for the plane CGHD, let's see the intercepts along the A basis. So it is 1 unit from A to D, that it intercepts in 1 unit. So the intercept on the A basis direction is 1. So M1 is equal to 1. Now, let us look at the intercept along the B direction. This is the B direction. And this is the plane here, the dotted plane. It never intersects with the B direction, right? It doesn't cut through the B direction. In fact, it is parallel. It's running parallel to the B direction. And we see that parallel lines or a parallel plane on a line will intercept at infinity. So M2 is equal to infinity. Similarly, M3 for C direction here, this plane intercepts with the C direction. Again, M3 is equal to, again, infinity, because it runs parallel. So now you immediately see why we take the reciprocal, because you can have planes running parallel to a basis vector, and you cannot use infinity. Infinity is almost undefined. So when we take the reciprocal of 1 is 1. The reciprocal of infinity is 0, which more meaningful than infinity. And the reciprocal of infinity here is again 0. So this plane is going to be the 1, 0, 0 plane. Okay, so this first plane is the 1, 0, 0 plane. Okay, now we also need to determine this plane ABFE. Here is A, B, F, E. But as you can see that if we take A as our origin, and we have all these vectors A, B, C here at A, we have lots of problems when we look at this plane here, right? This is the plane we're looking at, because this plane goes through the origin. One point goes through the origin, right? And all other basis vectors are actually sides for this plane. So that's why I told you it's not critical, to work with only one origin. So what we could do, we could extrapolate, go back, and then take a point here, lattice point here, which is immediately at the back of A, call it A dashed, and take this point as our origin. So this will be my A, here will be my B, and here will be my C. Okay? And now, if you do this, you can immediately see that this plane, okay, has intercepts, which are 1 along A, the same intercept here, M1A, okay? And then the same intercept here, M2 infinity along B, and M3 infinity along C. So the Miller indices, which are the largest, which is when you take the reciprocal and you take the smallest numbers, is again 1, 0, 0. So again, this plane here at the back is 1, 0, 0 plane. Okay, so this plane here is the 1, 0, 0 plane, and it's parallel to the plane CGHD. So they're all the same plane, 1, 0, 0. So in fact, all parallel planes to this plane, they will all be 1, 0, 0. So they are all called, 1, 0, 0 planes. So when we say a 1, 0, 0 plane, it represents one plane and all planes that are parallel to this plane. Okay, so that is these two planes, and here I tried to show you that it is not important, to choose one single origin. You can choose an origin that satisfactorily or easily describe the situation to you. Okay, now the next plane is EFCD. Let's see, E here, F up here, C is here, and D is here. So we're talking about this diagonal plane. Again, let's go back to our A as the origin, and let's look at the intercepts of this plane with the basis vector A. So that intercept is M1 equals 1. And then the intercept at B here, there is an intercept now. An intercept now at B is M2 equals 1. But there is no intercept along C because this plane runs parallel to the C axis. So M3 is equal to infinity. Then we take the reciprocal. Okay, so the reciprocal here is 1 for M1. The reciprocal for M2 is 1. And the reciprocal for M3 is 0. So the smallest integers in this ratio are the integers 1, 1, 0. And so this plane here is the plane 1, 1, 0. Okay? Now we come to the third plane, which is BED, which is this triangular plane. Now, as you can see immediately that this plane has actually, it has intercepts. If we take our A as an origin, it has intercept with the basis vector A, which is M1 equals 1, and it has an intercept with B, where we have M2 equals 1, and it also has an intercept with C, where M3 is equal to 1. So if we take the reciprocals, for M1 is 1, for M2 is 1, for M3 is 1. So this plane is going to be the plane 1, 1, 1 plane. Okay, so this plane is the 1, 1 plane. So now we have defined all the 3 or 4 planes. We found 2 of them that are parallel, are 1, 0, 0. And then we found this diagonal plane as the 1, 1, 0. And then we found this triangular plane as the 1, 1, 1. So we obtained the Miller indices for all the planes now. Then the next step, or the next question, is find the crystallographic directions A to F and E to C. So here we have E to C, right? But it's not A to F, it's A to G. A to G, actually. So let us call this A to G. Okay, so we have to locate G, position of G with A as an origin. So along the A axis, it is 1. Along the B axis, again, it is 1. Along the C axis, again, it is 1. So this vector has directions 1A plus 1B plus 1C, so the direction is 1, 1, 1 plane. And then let's look at EC direction, okay? Or is it, let's see, maybe this one is, oh, I'm looking at, the example is AF here, but I looked at, but the drawing is AG. The drawing is showing AG, but we can also find A to F. If we try to find A to F, which is this direction here, okay, then we have the point F, which has 0 in the A direction, and it has 1 in the B direction, and it has 1 in the C direction. So actually, the A to F direction is the direction 0, 1, 1. Okay, and you see that the direction, I put it in a square bracket to distinguish it from a plane, right? And then we can also go ahead and do E to C. Okay, and for E to C, actually, it's E to D. You see, again, the figure is not giving me the right direction, so it is E to D. So let's see E to D from this here to this point. So how do we do that? E to D is written as A to E, the difference between two vectors, A to E minus A to D. Let's go back and see if this is correct. Okay, so A to E, A to D, and A to E. So if you have this vector here, and we have this vector here, so if we need a vector E to D, which is this vector, then we know that this vector is the sum of these two vectors. So RA to D is the sum of RA to E minus RE to D. So indeed, this relation is true. RE to D is the difference between RA to E and RA to D. So if we write these vectors and make the subtraction, this is what we end up having. So these are the coefficients of the vectors. So we put these coefficients in a square bracket, but note one thing, because there is a minus sign here, I'm putting a minus sign on top of the first coefficient, showing that it's a negative direction. So minus 1 on top, 1, 0. That's the direction from E to D. Okay, so this is how we talk about single crystals. This is how we define planes in single crystals. And this is how we define directions in single crystals. This is how we obtain Miller indices. And this is how we obtain directions. So single crystals are only one type of crystals. The second two types, the remaining two types of solids or solid structures, are the polycrystalline and the amorphous solids. A polycrystalline, poly means many. This word poly means many. Polycrystalline means many crystals. Look at this drawing here, or this picture here, or this schematic here. You can see regular arrays of lattice points and actually cores, atoms sitting on these lattice points. So there is a single crystal here. And there is also another single crystal here. So we have a single crystal and another single crystal. The only difference from this structure and the single crystal structure that we discussed before is that these two single crystals are exactly the same structures, but they are oriented differently. There is a misfit in orientation. Okay, so they are oriented at in two different directions. And in between, there is a region which is not organized, which is not uniform. So each one of these single crystal sites is called grain or crystallite. They're all the grains are single crystals. But when they are connected by grain boundary, which is a kind of irregular part of the crystal. So a polycrystal means that more or many single crystals connected by grain boundaries, oriented differently. This is called polycrystalline. So you have some regularity in each grain. You have long range uniformity in each single grain. But if you increase the distances, you don't get the same uniformity because the grains are oriented differently. So this is the second type of single crystals, which is polycrystalline. The third type is amorphous. Amorphous meaning there is no regularity, there is no uniformity, there is no long range order. Everything is random. All points or cores are randomly distributed in space. This is called amorphous. Okay? And again, we get solids that have the amorphous structure. Okay? So, polycrystalline materials are, as their name implies, made up of many crystals, as shown in the figure. Each crystal has the same unit cell. However, the unit cells in adjacent crystals do not have the same orientation. So the crystals and unit cells in different grains are oriented differently. Any one particular single crystal region with its fixed orientation of the unit cell is also called or termed a grain. Hence, polycrystalline materials are made up of many grains. The transition region from one grain to another is called the grain boundary. That's the amorphous region, if you like, or the region that is not regular between grains. Grain sizes may range from tens of nanometers, very small. Nanometer is 1/1000th of a meter in some materials. And sometimes it goes to grains that are micro grain, 10 to minus 6 of a meter, and these are called microcrystalline materials. And in some cases, these grains can be as large as centimeters. Okay? So you can have different sizes of grains depending on the different solids. Crystalline and polycrystalline materials possess long-range order, but the long-range order in the polycrystalline material is terminated, at the grain boundaries. Okay. The third type of structure is, on the other hand, complete lack of such repeatable unit cell. You cannot get a unit cell and repeat it. Okay? And so therefore you cannot get unit cell of a fixed dimensions and orientation, just like we saw in the figure. So this kind of solid is called amorphous, and it has no long range order. So these are the three types of solids. Solids that are single crystals, solids that are polycrystalline, solids that are amorphous. Clearly, you can see that the most regular type of solid is the single crystal. And in electronics, we use all types of solids. We use single crystals, we use polycrystalline solids, and we use amorphous solids to form the devices. However, to understand the behavior of electrons in a solid or in a crystal, we are going to choose the single crystals because they are uniform, they are easy to study. And we're going to illustrate the properties of electrons in a single crystal. Okay? And that will help us understand the properties of solids.